Astronomers for Planet Earth is an organization of professional astronomers and educators dedicated to helping people understand the causes, consequences, and solutions for climate change. This webinar series brings in experts to share their work to help you, the listener, be better informed and able to make a difference. Our host is Dr. Travis Rector, an astrophysicist at the University of Alaska, Anchorage. Brian Siana is an associate professor of physics and astronomy at the University of California, Riverside. He's an observational astronomer studying early universe galaxy formation, reionization, and gravitational lensing. He's also the associate director of sustainability at UCR, overseeing sustainability curriculum and research and working to make the University of California more sustainable.
Hi, everyone. Today we have our guest speaker, Dr. Brian Siana, who is also an A4E member. And in his talk today, he will be talking about the roles that physicists and astronomers can be playing in helping to advocate for sustainability at home, at their workplace, and also in their communities. So thank you, Brian, for joining us today.
Thanks, Travis, for having me and for inviting me to do this. So for the last sort of 15 years, I've been getting more and more worried about climate change. And it's harder and harder to concentrate on only my astronomy research when such an urgent need is there to address our carbon emissions. So yeah, this is kind of a summary of my philosophy of how we can best reduce our carbon emissions quickly in our homes, but also at our institutes and our universities and around the world, really. And I kind of have a physicist take on this, so bear with me. So I'm not going to get into the details of this. We've had other talks about this, but ultimately climate change is an energy balance issue. We've got a lot of energy coming in, as you know, from sunlight. 30% of it is immediately reflected, but 70% of it's absorbed by the atmosphere and the surface. And of course, it's warm and it is re-emitting infrared radiation, but that infrared radiation is at some level being blocked or slowed by the greenhouse gases in the atmosphere on their way out, which is good. We would be a snowball Earth without it. But the problem is, of course, that we are adding the amount of greenhouse gases in the atmosphere. The worst one is carbon dioxide. And carbon dioxide has been dramatically changed recently. I love to show this plot because it shows not only the dramatic change in recent years, but the lack of change over 10,000 years. There's actually this remarkably stable period of 10,000 years where the carbon dioxide concentrations didn't change much at all. And therefore, the temperature didn't change that much either. And it's perhaps not a coincidence that this is when human civilization really began. We came out of, we created agriculture in this time, came out of the Stone Age into the Bronze and Iron Ages, and really modern civilization came about under these conditions. So this is 10,000 years in which all of our ecosystems were able to kind of stabilize and evolved to this stable equilibrium, and our infrastructure and our societies were set up under this equilibrium, right? And then a couple of hundred years ago, we realized that we didn't have to be limited by the work that an individual human could do, but instead could dig up a bunch of energy out of the ground in the form of fossil fuels, burn it, and do work a lot quicker with it. And we've gotten very good at that, and we've been burning a lot of it, and we are now up here somewhere. And I like to emphasize that our CO2 concentration has gone from something like 270, 280 to 415 or so right now. That's a 50% increase. This is not a slight perturbation. This is 50% increase in the amount of greenhouse gases in the atmosphere. And these are big numbers. 2.3 teratons of carbon dioxide have been emitted by humans in these last couple hundred years. 2/3 of that since I was born in 1977, right? really, we are transforming the Earth's atmosphere in a single human lifetime. And that has major implications, right? First and foremost, it's warming the planet. Everybody says, well, we've warmed about 1 degree Celsius in the last century. But what I like to emphasize is that it's almost twice as much on land where we happen to be and where we happen to be growing crops and where plants live and whatnot. And so I've converted to the Americans in the audience to Fahrenheit on the right, 3.5 degrees Fahrenheit over land. So it's not uniform across land and ocean. And more importantly, it's not uniform with latitude. And the Arctic has warmed 5 or 6 degrees Fahrenheit over the last century. And this has huge implications for the planet and ecosystems and infrastructure, weather patterns. But that is not what this talk is about. So scientists have been getting more and more concerned about what that temperature change and continued temperature change is going to mean for weather and the planet and whatnot. And the IPCC, the Intergovernmental Panel on Climate Change, came out with a report 2 years ago. This is through the UN, where they said, you know what, everybody's been talking about 2 degrees Celsius, keeping the warming to below 2 degrees Celsius globally. But more and more people are getting concerned about that number, that's actually a very scary number. We're at about 1 now. Another 1 takes things so much further away from equilibrium. Can we try to keep the temperature to warming to 1.5 degrees instead of 2 degrees? And the scenarios they put forward are very difficult for society, right? These are 4 scenarios for how we could keep temperatures to below 1.5 degrees Celsius. And they don't actually change that much. The gray shaded things are our emissions from fossil fuel burning each year over time from 2018 onward. The brown is agriculture, forestation, and land use, right? So that has carbon emissions associated with it. But if we let forests grow back, we can actually store some of the carbon. And then this yellow is BECCS, that's bioenergy and carbon capture and sequestration. This is growing immense amount of plants for energy, burning them, and then sequestering burning them for our energy usage, and then sequestering that carbon underground at scales that we simply do not know how to do. These are tens of gigatons of carbon every year for decades or a century put underground. We do not know how to do this yet. So, maybe we'll look at this scenario here, but it doesn't really matter. What this means is our fossil fuel burning, really in any of these scenarios, has to fall off a cliff really quickly. Globally, our CO2 emissions need to decline, our annual emissions need to decline, be cut in half in the next 10 years. This report came out in 2018 and it said by 2030, we need to decrease our emissions by half, right? This is everything that that humans depend on needs to come down by a factor of 2. That's a radical change. And if I were betting, I would say it's probably not going to happen. But there's nothing special about 1.5 degrees Celsius. It's not like after 1.5 degrees, the Earth spontaneously combusts. Every 1/10 of a degree Celsius is bad. And we should try to prevent each additional 1/10 of a degree, but there's nothing magical about 1.5. So maybe we can keep it to 1.8, or maybe we can keep it to 2 degrees. But nonetheless, even a 2 degree scenario, 2 degree warming scenario, just delays the reduction in carbon emissions by 50%. Sorry, it just delays that reduction that we need of 50% reduction in carbon emissions by a decade or so. So instead of 10 years, it's 20 years. That is still a really, really hard thing to do. And we should probably not delay, because the more we delay, the faster the reduction needs to be after that. And this has big implications, the speed at which this has to be done, for what the possible approaches we take are. And what it really means is that we need transformation, not just efficiency. Efficiency is good, it's great, but we do not need to be focusing solely on efficiency anymore. We need to be fundamentally changing our sources of energy, transforming our energy systems. Saul Griffith, a physicist and entrepreneur, he says, we can't efficiency our way to zero, and we need to get to zero. Fundamentally, many of the places where we emit carbon, where we use energy in our society, they have fundamental limits to their efficiency, and we need to get below that to fundamentally zero emissions. You can't drive a 2-person wide car at highway speeds and get more than 70 miles per gallon, right? There's drag force, there are thermodynamic issues with the heat engine in the car, and we're not going to efficiency our way to zero there, right? You can't get more light out of an LED bulb because LED bulbs are converting all that electrical energy into light we see. That's the point of the bulb. You can't efficiency your way to zero. So we need energy that comes from non-carbon emitting sources, right? And another point about the timescales of this reduction is that we have 10 years or maybe 15 years or something like this to reduce these emissions by half. That means we have 0 years to start, right? We have to start now. And that is because a lot of the things we need to switch out have lifetimes of that 10 to 15 years. Vehicles, our cars last 15 years. If we buy an internal combustion engine today, in 15 years, it will still be emitting the same amount of carbon. Our appliances, 10, 15 years, right? If we're lucky. Air conditioners, or HVAC in general, heating as well. We swap these things out on, 10, 15-year timescales. So for every one of these things, when we replace them, we need to replace them with something that allows us that functions without emitting carbon into the atmosphere. Then we can naturally decline on our way to 2035 or so with radical reductions in emissions associated with these things. And delaying this further means we need to act faster after our delay. And that means all of a sudden we need to now replace things before their natural life cycle is up. And that means it's far more expensive, right? So we need to start today. So if you're thinking of buying a new vehicle, be careful, right? All right, so I apologize to the non-Americans. This part of it's a little American-centric. But nonetheless, each country has, in the, in Europe and Australia, Japan and China and all, they have similar figures. This is a map of all of the energy consumed in the United States. It's in really unfortunate units, quads. This is quadrillion BTUs. But whatever, it's 10 to the 20 joules. That is that's the amount of energy that Americans consume. And the really nice thing about using this weird unit is that there's 100 of them because all of these associated numbers here are in the same unit, and it's about 100. You can look at these as percentages, and that's kind of convenient, okay? Oh, by the way, that's a gigajoule per person per day in the United States. We are a very high energy society. And okay, so let me break down this figure because there's a lot going on. This is produced by Lawrence Livermore National Lab. On the left is all of the sources of our primary energy. And basically, and as you can see, this mostly from fossil fuels, 37% from oil, 11% from coal, 32% from natural gas. And then there's these pipes, and the thicknesses of the pipe is how much is going into each sector. 37% of the energy goes into generating electricity, 28% or so goes into transportation, 26% into industrial, and about 10% each into residential and commercial buildings. And then one thing to note on here, is that It also shows the rejected energy. These gray bars that are coming along here are energy that isn't ultimately used. It's completely wasted and doesn't go to providing the services that we actually want. 2/3, right? 67% of all of the energy is completely wasted. We might want to change that. And so you might ask, how is this, all wasted? Where is this coming from? And there are these two huge gray pipes coming into this that are providing most of the wasted energy: electricity generation and transportation. These are fundamentally inefficient, and the vast majority of the energy is wasted. Why is that? It's because they're heat engines. In your physics class, intro thermodynamics class, you probably learned all about heat engines a long time ago and forgot about it. But heat engines are simply, inputting thermal energy in order to create mechanical work, which is often what we actually want, right? But these are typically very low efficiency, right? It matters on how hot you burn the thing, but they're low efficiency. You all remember the ideal Carnot efficiency, the amount of mechanical work you can get out for the amount of thermal energy that you put in. And it goes as 1 minus the ambient temperature divided by the hot gas that you've created by burning fossil fuels. But none of these systems, none of these systems are actually burning anywhere near Carnot efficiency. But even if they are, they're fundamentally inefficient because we're going from, second law of thermodynamics, we're going from some disorganized energy to organized energy. And transportation was one of those big sources of wasted energy. That's because we're using internal combustion engines. We are burning fuel in these 4-stroke engines to create mechanical work to move our cars, but we are using heat to do it. Gasoline engines are about 20% efficient in converting the chemical energy and ultimately the heat into mechanical energy. So 4 out of 5 parts is wasted out the exhaust pipe or to heat the engine block. Diesel engines, they burn at higher temperature and pressure. They're more efficient, but still they're wasting a vast amount of their energy. And electric power production, like steam turbines, same thing. Coal power plants are about 30% efficient in their conversion of heat to electricity. And natural gas power plants are better. They burn at higher temperatures. And depending on the type of plant, you can get 50 to 60% efficiency in conversion to electricity. But still about half is wasted. So ideally, and I just want to emphasize, these are using heat when we don't actually want heat, right? And that's fundamentally inefficient. And I want to point out where that heat is coming from. The electricity generation, the majority of that electricity generation is coming from natural gas, and it's coming from coal. These are fossil fuels that when we burn them, they are producing carbon dioxide. The transportation sector, those internal combustion engines in our vehicles are powered by oil, right? Gasoline or petrol, I guess, if you will. So not only are these inefficient, but they're actually the sources of our carbon dioxide as well. And so this is all an energy map, but I can instead talk about the carbon dioxide, break down the carbon dioxide, right? These are US greenhouse gas emissions from each of these sectors, okay? And the biggest 2 pieces in green here, 30% is transportation. And the second biggest is the blue sector here, 26% is electricity, where these heat engines, so the majority of our carbon dioxide emissions come from these heat engines when we don't want the heat. So maybe we should use something else to create those, to do those things. So for electricity production, we have lots of alternatives, of course. You're familiar with them. We can produce electricity directly from the sun. with photovoltaics and solar panels. Wind onshore and offshore, this is really growing rapidly. We can use hydropower. We can even use hydrogen fuel cells to create electricity. There are lots of options to create electricity without using heat engines. Note, I will allow some heat engines because they don't emit carbon dioxide. Yes, they're fundamentally inefficient, but nuclear or geothermal heat engines produce electricity, and I'm all for it if it's not emitting carbon dioxide. And we are doing this, right? In California, 58% of our electricity is from carbon-free sources of energy. A little bit of nuclear, a little bit of hydro, a little bit of solar, a little bit of wind, all added up together, it's about 58%. So we're really getting there. And it's going to increase each year as mandated by law in the state. So alternatives to heat engines on the transportation side, it's pretty straightforward. If we've got clean electricity, like in the previous slide, we can use that clean electricity to power our vehicles, not with internal combustion engines, but with electric motors. So once the electricity is clean, or as it's getting cleaner, we can use it in electric motors. The efficiency is really, really high in these electric motors, and the amount of the conversion of electrical energy into mechanical energy, greater than 90%. Even charging the battery and discharging, it's still great. It's about 80% now in these newer vehicles. And I use examples here. This is my car. It's a Hyundai Kona electric. In America, people like to drive trucks. This is the Rivian. This is in collaboration with Ford. And then even in short distances, actually shipping can be electrified. And so Tesla is trying to do this, as well as other people as well. So, there are big advances that could be done here. And in fact, they're being done. I own this car. These electric motors are wildly simpler than internal combustion engines. They typically have 20 moving parts instead of 2,000. I know that sounds crazy, but there are no pistons. There's no oil. There's no oil filters. There's no valves. There's no timing belts. There's no exhaust systems, no radiators and cooling systems. It's so much simpler. They're cleaner, right? There's no exhaust at street level where people are, so there's no pollution there. And there's no CO2 associated with it if you're using clean electricity. They're quieter, they have better torque, they're lower maintenance, and the cost per mile to drive them is much lower. That depends where you live, the cost of your electricity versus gas, but it's about 30% of the cost per mile of an internal combustion engine for the same type of car. So obviously there are details there that I'm brushing over because it's a short talk, but that was dealing with these transportation electricity sectors and all the waste there. And the fact that we don't want heat engines because we don't want the heat. Now I'm going to say something a little weird. A lot of our natural gas usage and some other fossil fuel usage is going here and here into our buildings. And that is producing CO2 when we burn it. And we are burning it for heat. So now we are burning this stuff for heat's sake, not in order to get work out of it, mechanical work out of it. And what I'm about to say is that even that is a bad idea. Making heat for heat's sake is inefficient, even though it's almost 100% efficient. What am I talking about? Oh, by the way, that is this wedge in the carbon dioxide emissions of the United States. About 10% of our emissions is from space and water heating in our buildings. So why don't I want to use heat from natural gas to heat this? Well, we have alternatives that are actually much more efficient and give us a pathway to reducing our carbon emissions, okay? The better solution is using not heat engines, but reverse heat engines, okay? And those are called heat pumps. And this is where we're using mechanical energy in this case, typically driven by electrical energy, to move heat from one location to another, okay? We have heat pumps in our homes now. Our refrigerator is a heat pump. Our air conditioners are heat pumps. They are moving heat from a colder climate out into a warmer climate, right? We can actually have a heat pump that moves heat into our homes in the winter, right? And in fact, our air conditioners can be heaters. All we have to do is reverse the flow of the refrigerant. And they're very, very efficient. Again, we're harnessing the second law of thermodynamics. We have a form of energy in electrical energy that is highly ordered, and making disordered heat, thermal energy, can therefore be more efficient. And in fact, we can get 3 to 4 times typically more thermal energy out of a heat pump than the electrical energy required to run it. So it's wildly efficient. And on top of that, we can use clean electricity from solar and wind and geothermal and so on. Now, it's worth emphasizing the magic of heat pumps here. This is how an air conditioner works, right? You have the home here. I just drew a little home. You have some cold refrigerant going through a coil, and you blow air over it, to, depositing energy into that refrigerant. And then you compress the refrigerant, which heats it up. And then you blow air over it outside to take away energy. And then you allow it to expand again, to cool, and so on. And this is how we move heat out of our home to air condition it. But of course, if you just put the home over here, you can do the opposite, right? You can move heat into your home in the same manner. Of course, every beginning of summer and every beginning of winter, we don't actually want to move our home, and we don't want to, repipe this stuff. There's a simpler way to do this. And I feel like talking to the Europeans, they're like, yeah, we know this already, but most Americans don't know this. You can actually keep your home in the same place and instead put a little valve here, a reversing valve that says, oh, they want to cool their home, great, go this way. Oh, they want to heat their home, go this way, go through the compressor right before it goes through the home. So that sounds ridiculous, but the thing that is your air conditioner now can be your heater, and it's very, very efficient, and it can use clean electricity, right? So we should be using heat pumps for all warming. Notice I say warming, not heating. That's because heat pumps are really efficient when you're providing warm air. They're not efficient when you need really high temperatures, right? Like hundreds of degrees. But space heating, right? Central air conditioners, we can just swap them out as soon as we need to replace them. There are so many examples. In the American South, there are 28 million homes that use electrical resistance for space heating, just running current through a wire, heating it up, and have it heating up the surrounding area. That's really bad use of highly ordered energy. All of that's in the American South. They all have air conditioners, and those could be swapped out with heat pumps and get rid of this inefficient electrical heating, right? Yeah, and water heating, the same thing. We have 110 million water heaters in the household water heaters in the country. Almost none of them use heat pumps. They either use natural gas or electrical resistance, which is just a very inefficient way of using electricity. We can swap those out upon replacement. All right, so putting it all together, removing heat engines, we can get a 56%, probably not that much, but something like 50% reduction in carbon dioxide emissions. Installing reverse heat engines, heat pumps, to heat our space and water reduces further our reductions another 10%, right? So combined, that's 2/3 of our carbon dioxide emissions with existing technologies and replacement of cars and furnaces and whatnot at end of life. So it's not that expensive, right? Or to put it in meme form, heat engines are bad, reverse heat engines are all right, okay? So if you're still paying attention. All right, anyway, and I'll just add one point. This strategy of electrifying all of this stuff really helps us put us in in a place where we can actually address most of the rest of the emissions in this pie chart. In this scenario, we're going to have a whole bunch of solar, a whole bunch of wind, and these are intermittent. And sometimes we're going to have too much of it. A lot of the time, we're going to have too much of it. We literally turn off 6% of our solar production in California now because we have too much of it certain times of the year. We can use that excess electricity to create hydrogen via electrolysis and use it for high temperature applications. And that is what this red wedge is here. This is industrial heat used for steel production, cement production. And so now we have a pathway to provide a clean source of a high temperature heat for most of the rest of the wedge, right? And Europe is really starting to embrace this. California sort of starting to embrace this. We'll see how it goes, but it's an interesting path. Okay, so reorganize for non-astronomers and non-physicists. Really what this means is we need to clean the grid, electric grid, and we need to expand it because we're going to be putting a lot more demand on it. And at the same time, we need to electrify everything. We need to electrify our heating. We need to electrify our transportation. And that is really the strategy of a lot of people in the United States and in Europe as well. One of the groups, if you are interested, is called Rewiring America. It's run by a physicist. And their whole goal is expanding the grid and cleaning it and converting everything to electricity. So this also, okay, so I've done this in my own home. I put 10 of these generic low efficiency solar panels on my home, and I get electricity without heat engines. This is my car. I get my transportation without a heat engine, and the electrical energy that I use is very clean in terms of carbon dioxide emissions, partly because of my solar panels, but because I get energy from the California electric grid. This is my air conditioner that I replaced 2 years ago. It has a reversing valve in it, so it heats my home also. And because it's doing twice as much work, I was incentivized to get a more efficient one. So I'm running out of time, I think, but how do we do this? We need to overbuild renewables. Wind and solar are actually the cheapest forms of electrical energy in most places in the world now. I mean, we're getting 2 cents per kilowatt hour power purchase agreements now. At that level, you just build more. Yes, you might have too much of it 10, 20% of the time, but at that cost, who cares? You want to diversify your renewables, right? A lot of places in like in the American prairie, you know, Texas and whatnot, they have a ton of wind, but they also have a solar resource and they haven't taken advantage of it. Diversify, add geothermal. Maintain our existing nuclear fleet. This goes for you, Germany. This goes for you, Japan. We have existing nuclear power plants. We should not be shutting them down. And we need a national grid. We need to share our electricity on physical scales that are much larger than weather patterns, right? That way, we smooth out fluctuations due to cloudiness causing disruptions in solar or lack of wind in one area, right? Everything gets much smoother if you expand the size of the grid to be much larger than a typical weather pattern. Yeah, we need high voltage DC transmission lines. We need to store some energy and batteries in the short term, but hydrogen in the long term for seasonal storage. Every new vehicle is an electric vehicle. Every new water heater and every new air conditioner is a heat pump. Yeah, but actually, how do we do all that? I don't know. And this is the problem. This is fun. This is my last slide, by the way. This is fundamentally the issue. We do not need new physics. We do not need to be in a lab inventing new things. We have the technology. What we don't necessarily have is the social movement and the political pressure, right? We need to we need social movements. We need to help and listen to marginalized communities that have been dealing with environmental degradation, right? It is very, very hard for people who are dealing with pollution in their air and water to get them interested in climate change when they're far more interested in pollution, right? We need to bring them into this tent and address their issues first and foremost. And often they're the same issues. Environmentalists need to allow big developments to happen again. I think environmentalists have been saying no to big things for many, many decades, but we need to build high voltage transmission lines across this country. And environmentalists love saying no to those things. I'm an environmentalist, but we have to start saying yes to some big things again. Obviously we need some smart policy, and it's weird, but a lot of this can be fixed with financing. It's very out of the realm of the physics and astronomy space. And so it's a little strange to say, but get involved with social movements, get involved addressing other environmental concerns, get involved with policymakers. This is where this is going to happen. But the take home message is that we have the technology to address most of this in the 15 years. And that's not even using less energy, like, making our homes better insulated or anything like this. I have not even mentioned that. We need to start today. And we need a, World War II level effort, scaling up all of these changes to mitigate climate change on this time scale. And it's going to take moving policymakers and people with funds to do this. So that's all I have to say. Thanks.
Well, thank you, Brian. That was fantastic. I know I learned a lot, and I look forward to all of the questions that our audience will have for you. So thanks again for what was a really interesting and inspiring talk.
We hope you've enjoyed today's talk. Each of our talks is followed with a Q&A session that you can learn more about in the video description. If you're interested in Astronomers for Planet Earth, you can learn more at our website, astronomersforplanet.earth, and on social media as well. If you would like to be notified about future talks and events, please follow and join us.